Hey everyone, welcome. Today we are going to tackle a real classic, one of those problems that can feel super tricky at first glance, Irodov 1.73. So let's just dive right in and crack this code together.
Have you ever had that moment you flip open a physics book and bam, there it is, a diagram that looks like a total mess of pulleys, blocks, and strings all tangled up? It honestly looks more like something you'd see in a modern art museum than a problem you're supposed to solve. And right away, it's easy to feel totally overwhelmed, you know? Like, where do you even start with something like that?
Well, today we're not backing down. We're going to tackle one of those very problems head on. We're diving into problem 1.73, and this one comes from a legendary book. A book that's basically been the boot camp for physics and engineering students for decades. The one and only I.E. Irodov's Problems in General Physics. You know, for generations of students, just hearing the name Irodov is enough to make you sit up a little straighter. His book, it's legendary. It's not just some random collection of problems. It's really a rite of passage. It's designed to forge that deep physical intuition right from the very beginning.
So here's the challenge laid out for us. We've got this system with three different masses, M0, M1, and M2. And the setup is pretty ideal. They tell us there's no friction, and the pulleys and threads don't have any mass. Perfect world, right? Now, the actual question seems simple enough to ask, but it's a whole other story to solve it. Our mission? Find the acceleration of just one of those bodies, M1.
Okay, so how in the world do we even approach a beast like this? Do we just start scribbling down every equation we know and hope one of them works? Absolutely not. There's a much smarter way. And the secret weapon, the real key to unlocking these Irodov problems, well, it's been hidden in plain sight this whole time. It's right there in the preface of the book itself. Yep, Irodov himself lays out the master plan for us. He says, and this is so important, solve problems in their general form. That means using letters, variables, not just plugging in numbers right away. And this isn't just to make it look fancy or academic. No, doing it this way actually reveals the deep physics at play. It lets you see the relationships, and it gives you a way to test your final formula that you just can't get with a single number. And that is exactly the strategy we're going to use today.
So here's our game plan. It's a clear, four-step process. First, we're going to deconstruct the problem, break it all down. Second, we'll build the equations in that general form we just talked about. Third, and this step is absolutely crucial, we're going to do some sanity checks to make sure our logic holds up. And finally, we'll wrap it all up by turning this method into a powerful toolkit that you can take with you to solve pretty much any problem.
All right, let's get into it. Step 1, deconstruct the problem. Before we even think about writing a single F equals ma, we have to really, truly understand what's going on in this system. That means we need to identify every single object, every single force acting on it, and, this is key, every constraint that ties them all together. Okay, let's trace out these forces. For our first mass, M1, you've got gravity, M1g, pulling it straight down, and you have the tension, T, from the string pulling up. Simple enough. Same exact story for M2. Now let's look at the wedge, M0. See how the string wraps over it? That means it's getting pulled from both sides, which creates a net tension pulling it horizontally to the right. And here's a pro tip. For now, we're just going to assume a direction of motion. If our final answer comes out negative, no big deal. It just means it's moving in the opposite direction. Easy. Okay, now for what is honestly the trickiest part of this whole problem. This is the hitting rule, the thing that connects everything together. And I'm telling you, this is where most people get stuck. Here it is. The motions of these three blocks are not independent. They can't just do whatever they want. They are literally tied together. Because that thread has a fixed length, when one thing moves, the others have to move in a very specific, coordinated way. And that relationship has a name. It's called a kinematic constraint.
So what is a kinematic constraint? It's basically just a rule that describes how different parts of a system have to move in relation to each other. Think about it like this. For every inch that wedge, M0, scoots to the right, it has to let out or feed that same amount of string to the two hanging masses, right? That means its horizontal motion is directly linked to the average vertical motion of M1 and M2. Nailing this relationship, getting this one equation right, it's the absolute key to solving this whole thing. Okay, great. Now that we have a solid physical picture in our heads, we can move on to step 2. It's time to translate everything we figured out into the language of math. We're going to build those equations in their general form, just like Irodov told us to. So let's apply Newton's second law, good old F equals ma, to each of our bodies. For M1, the net force is gravity pulling down minus the tension pulling up. So M1G minus T equals M1A1. The equation for M2 is going to look exactly the same, just with a subscript of 2. Now for the wedge, the only horizontal force is that double tension, 2T, and that equals M0A0. And then we add our secret weapon, that kinematic constraint we worked so hard to find. And look at what we've got. 4 equations and 4 unknowns, A1, A2, A0, and T. And you know what that means? It means the system is totally solvable.
But hold on, before you dive headfirst into a mountain of algebra, we're going to follow another piece of Irodov's brilliant advice. We're going to test our setup. We're going to look at some simple extreme cases and see if our equations give us answers that actually make sense in the real world. This, my friends, is how you catch your mistakes before they happen. So let's try one. What happens if the 2 hanging masses are equal, so M1 equals M2? Now, your first instinct from looking at simpler pulley problems might be to say, oh, it's balanced, nothing moves. But that's where the wedge comes in. Our system of equations will actually show us that there is an acceleration, and that little surprise forces us to remember that the wedge, M0, is part of the action too. Its inertia is a factor. Okay, what about another extreme? Let's say M1 is gigantic, and the other 2 masses are practically 0. What should happen? Well, M1 should pretty much just drop like a rock, right? It should be in free fall. So our formula for its acceleration, A1, should get really, really close to G. See? This is how we test if our logic is sound.
Just pause and think about that for a second. When we do these simple checks, we're doing more than just trying to catch mistakes. We're actually building up that deep physical intuition we talked about. We're getting a feel for how all these different variables are connected, how they affect each other. We're basically confirming that our mathematical model of reality actually behaves like reality, at least in these simple cases. So, now that we've deconstructed, generalized, and checked our work, the final step is the calculation itself. It's really just algebra from here on out. You take those 4 equations we built, and you play a game of substitution to isolate our target, A1. Yeah, it's a little bit of work, but the hardest part, the physics, the actual thinking, is already done. So let's zoom out and look at the powerful method we just used, our problem-solving toolkit. And there you have it. This is the Irodov method in a nutshell. It's a 4-step toolkit you can bring to any complex mechanics problem. First, you deconstruct, break down the physics. Then you generalize, use variables to build your equations. Then you check, you test your logic with simple cases. And only then, only when you're confident in your setup, do you actually calculate the answer. This whole process makes sure you understand the why behind the problem, not just the what of the final number. And look, this method isn't just for solving this one problem. This is a universal problem-solving skill. You can apply this exact same approach to analyzing circuits, to thermodynamics problems, to engineering design, really any field where you have to take a complex system and model it with math. By being this systematic, by always checking your assumptions, you stop just being an answer finder and you become a true problem solver. You start to truly understand how things work. So, the real question is, where are you going to use this powerful approach next?